Hello and Assalamu alaikum. My name is Mirza Haider Ali Beg, and today the topic of my presentation is logic gates. So, the first thing that we're going to go over are the things that we will be covering in this presentation. The first thing is our logic gates, then representation of logic gates, AND gate, OR gate, NOT slash inverter gate, NAND gate, NOR gate, XOR or exclusive gate. These are the things that we're going to cover in this presentation, and that after the XOR gate, we're going to end our presentation. So the first question is, what are logic gates? Well, a logic gate is an idealized or physical electronic device implementing a Boolean function or a logical operation performed on one or more binary inputs that produces a single binary output. Such examples of logic gates are AND, OR, NOT, NAND, NOR, XOR, etc. Logic gates can be described by several symbols, including mil slash, ANSI, IC, and DIN symbols. The next thing that we're going to cover are the representation of logic gates. As you can see in the above figure, that we've got some representations of logic gates, which include the DIN symbols, the mil slash ANSI symbols, and IEC symbols. So to your leftmost image, we have our DIN symbols. In the middle, we have our mil symbols, and to the right, we have our IEC symbols. The most common one that we use in our course are the mil symbols, but we also occasionally use the IEC symbols. So now we're going to go on to the actual gates, and the first one that we're going to cover is the AND gate. So the AND gate is a basic digital logic gate that gives a high output, high or 1 output result only if all the inputs to the AND gate are high. This gate is used just for logical conjunction. The general expression of an AND gate is X is equals to A dot B or A or B combined. We can say that it is somewhat similar to the multiplication that we do in simple algebra. AND gates are available in IC packages. The 7408 IC is a well-known quad 2 input AND gate. If we are to look towards the image, we can see the representation of the logic gate of the AND logic gate, and also its truth table. As you can see that all of its outputs are low or zero if even one of its input is zero, and it is only high or one if both of its inputs are one. The next gate that we're going to cover is the OR gate. The OR gate is a basic digital logic gate that gives a high output if one or all the inputs to the OR gate are high. This OR gate is used for logical disconjunction. The general expression for an OR gate is X is equals to A plus B, or like simple addition as used in simple algebra. OR gates are available in IC packages. The 4031 IC is a well-known 4 independent 2-input OR gate. If we are to look at the image, we can see the representation of the OR gate and its truth table. By observing the truth table, we can see that if even one of its input is high or 1, the output will always be high. But to get a low output, you need to have both of its inputs at low or 0. Okay, so the next gate is the NOT gate, and this is probably the most basic gate of all the gates. The NOT gate is a basic digital logic gate which changes the state of the bit. It is also known as an inverter. It is used for logical negation. The general expression for a NOT gate is X is equals to A bar. A NOT gate is embedded into a NAND or NOR IC, among others. So if we are to look to the image, we can see the representation of a NOT gate and its truth table. So what a NOT gate basically does is that it switches the state of a bit. If the state of the bit before the NOT gate is 0, then after the NOT gate, its state will change to 1. If before the NOT gate, the state is 1, and after the NOT gate, its state will be 0. So it just basically inverses the state of the bit. The next gate is a NAND gate, or we can say that it is just uh, a NOT gate attached to an to a AND gate. So a NAND gate, not AND, is a logic gate which produces an output which is low only if all its inputs are high. It is basically the complement of an AND gate. The general expression for a NAND gate is X is equals to A dot B parenthesis and then bar. A NAND gate is also known as a universal gate as it can form all the basic logic gates. Now, this topic I could not touch upon because the universal gates topic is given to another student from my class. A NAND gate can be used by the 4011 IC, which implements four independent two-input NANDs. So if we are to look at the image, we can see the basic representation of a NAND gate and the truth table of a NAND gate. We can see that uh, its state will remain high only if there is a single low output, and its state will remain zero or low only if both of its inputs are high. So it is just basically the converse or inverse of the AND gate. Okay, so the next gate is the NOR gate. The NOR gate is also like a NOT gate attached to an OR gate. So a NOR gate, NOR OR, is a logic gate which produces an output which is high only if all its inputs are low. It is basically the complement of an OR gate. The general expression for a NOR gate is X is equals to A plus B and then inverted. A NAND gate is also a NOR gate is also known as a universal gate as it can form all the basic logic gates. A NOR gate can be used by the 4001 IC, which implements four independent two-input NORs. There is a typo in my slides right now, so we'll just consider these as NOR. Okay, so if we are to look at the image, we can see the basic representation of the NOR gate and its truth table. In the truth table, we can see that it will only give an high output if and only if both of its inputs are low. Otherwise, if there is even a single high input, then its output will always be low. The next gate that we're going to discuss is the XOR gate or the exclusive OR gate. The XOR gate is a digital logic gate that gives a high output when the number of high inputs is odd. An inverted XOR is known as an XNOR. It is also known as an exclusive gate in addition to XOR. The algebraic expression for XOR is X is equals to A dot B bar plus A bar dot B, or X is equals to A plus B parenthesis dot parenthesis A bar plus B bar. The logic symbol of XOR is quite different as it is a plus enclosed inside a circle. So if we are to look towards the image, we can see our XOR, the basic representation of a XOR gate and its truth table. In the truth table, we can see that it can only give a high output when the number of high inputs is odd. Otherwise, the uh, output will always be low. So to conclude my presentation, I would like to give an example circuit which showcases how we can make logical circuits from logical gates. So over here, we've got an equation of A and B or C bar parenthesis and D, and the whole equation is then inverted. So we can see that we have attached all the logic gates required to make this equation using wires. So this is the basic overview that I could give of digital logic gates, and I thank you all for listening.